Good morning. Yeah, am I good to go?
Yeah. Yep. Can you
Right.
say good morning back?
Good morning.
Thanks. Bear in mind I can't hear a single person there, so this is a bit...
Can you hear me? Can you hear me?
Okay.
Hey,
Yeah, I can hear you.
Okay, so you're only going to be able to hear me, I guess, not them. I'll have to repeat questions. Go ahead and go.
Okay, I mean, I'll be around after this session. I'll be available on IRC and Google Plus anyway. If anybody's got any serious questions that are going to take a long time to answer. So anyway, good morning, Austin. My name's Ellie. I'm mostly famous for doing really mad shit with Ruby. But today I'm here to talk to you about my current obsession, which is doing mad stuff with Go. And this is going to be a bit of a fast-paced presentation. For one thing, I'm going to try and teach you the whole of Go in one go. It can be done in 3 minutes and 40 seconds. I did it at RubyConf last year as a lightning talk. But today we're going to try something a little clearer. It's a very large slide set. I apologize in advance. It is available off SlideShare later, and it should all make perfect sense. So without much ado, Google Go. I think we might be missing... hold on a sec. I'm having the problem I always have with Keynote. I've collapsed things at the side, and those things at the side don't want to show themselves up. So let's just make sure I've got all of this open. Oh God, it's not possible to just open all, is it? Okay, we'll forget about that. Come on. Go on. Back to, oh yeah. I'm completely lousy at presenting, so please forgive me. Okay, I'm going to talk about Go, and I'm going to talk about it a little bit in the context of Ruby, and then I'm going to go off on a bit of a tangent later to show you what Go is really like as a language. So I'm going to start by comparing the two languages, because a lot of people think Go, being a statically compiled language, must be very unlike Ruby, a lot more like C or Java. And actually, they've got quite a few things in common. So, you know, they've got a very different compilation model in that Ruby isn't, it is compiled, but it isn't. You know what I mean? It's an interpreted language as well. But they've both got garbage collection, and they're both into strong typing. And they both also have a very dynamic type system. So we're going to start off by looking at that. So first off, Go is very minimalist. This is every single keyword in the Go language. A couple of them do some organization in files, declarations of types, and basic control flow. We will meet all of these as we go through. It's also very minimalist in terms of types for a low-level language. It's got a whole pile of numeric types, but really it's just got the value types, which are immutable, some reference types, which are what you mostly program with, which are very mutable, and I called them invocation types because I hate putting the word function twice in the same column, row. But basically, it's got proper closures, and it's got methods that are bound to types. So this is a very simple Go program. You know, it shows off the fact that it's a program, so it's got a main function, and it lives in a main package. It's got an import, which means it loads stuff in from another package. And there's an example of how it's actually used. That's called a selector, where it's actually being used there. Oh my God, I've got mouse pointer control. So I wasn't expecting that, so this might be easier than I thought it'd be. Constants, variables, there's really nothing really to talk about there. Now I'm going to start off by explaining very badly and inaccurately how type works in Ruby, because to really understand why Go and Ruby are quite similar languages, you have to understand a little bit about type systems. And this isn't going to be mathematical, and I'm going to use code, and I've got some diagrams, and the diagrams hopefully make sense. So this is a simple bit of Ruby. We've got a class for a counter. We've got a class that inherits for it called double counter, and then there's an example of using it down below. So in general, in a Ruby program, you will have an instance class. That's the class that actually describes the instance of an object you're playing with. Are we going to get a click through? Right. So here, double counter, that's an instance class. You've also got an inherited class. Great, I'm getting messages from Skype now. Okay, you've got an inherited class, and that basically allows you to pull in a whole pile of behavior from other classes in an inheritance hierarchy. And out of the two of them, right, here's an example. Counter is being inherited by double counter. Out of the two of them, you then get an expressed type. That's what the type of the actual object you're playing with at any one time. Now, we don't normally think about type in Ruby this way, but yeah, that's so that we've got something to compare to Go. And you know, we've got various things we can do. Here's an example of getting a superclass of something. You know, you've also got these modules that you can import, and modules effectively modify the instance class, the inherited class, and as a result, you get multiple inheritance in a sense. Now, effectively, when you've got a Ruby program, you send a message to an instance, and out of the other end, apart from the action you actually get or the data manipulation you get that you were looking for, you also get proof that a type has been asserted. And that's very important because, well, Ruby doesn't care about type assertion at all, being a message passing language. Go is fundamentally about type assertion. So we'll see a lot of examples of that later on. So Ruby's basically well, a couple of years ago, I got in an argument with someone on Ruby core, one of those trolls who likes to move in and say, we need all kinds of static typing in our language. And I came to the conclusion during this argument that basically Ruby is the quantum mechanics of programming languages, because absolutely everything that can change behind your back without you noticing can change behind your back without you noticing. So it's a very strange type system. So we've got instances of their own classes, and all classes are mutable at runtime. So every inheritance pathway in the language can be tampered with, which makes Ruby incredibly flexible. That's where we get our DSLs from. That's where we get all of our nice higher level metaprogramming from. But it results in type uncertainty, and that really bugs computer scientists. I mean, I come from an embedded systems background, so on the one hand, I'm used to playing with very, very static languages, but on the other hand, also doing very dynamic things with them, because you have to control hardware. And over the years, I've had so many arguments with computer scientists about the stuff that we take for granted in Ruby, that many people who maybe believed all those books by Nicholas Wirth a bit too much, believe is absolute anathema, no way to write programs. So, you know. Now, type in Go is different. It's different to type in Ruby. It's also different to type in C++ or Java. So this is a simple example of creating your own type. Go comes with primitive types baked in, but every primitive type can be co-opted to be your own custom-defined type. And that custom-defined type has methods. So you have a type system that says there's a memory layout, which oops, we've gone slightly out of order with the code slides, but never mind. You've got a memory layout and a method set. Now, the method set there, that add is a method that belongs to any pointer to the integer that I've defined. And if we go back, just here, that just says that I've defined a type int based on a physical type int. And so I can add methods to it. You can't add methods directly to a primitive type, but you can do this. You can just reuse the memory storage that they provide. So, oops, we're going the wrong way. This is actually very difficult, presenting this sort of stuff from across 4,000 miles. Now, from the combination of memory layout and method set, you get a static type. So far, we haven't done anything that would make a Java programmer or a C++ programmer feel unhappy. And that's what that is basically the description of a type in code. But now it gets a little more interesting. Now, here, I'm actually defining a type, buffer, that is actually composed, its memory layout is a slice, which is a window on an array, And all of the elements of that are our user-defined type int. Right? And this is the method set that goes with that. Right? So, and together they comprise a type. But if we look down, here, this is an example of actually using it in a program. So this here is called a selector. And so we're selecting the buffer type from the package integer. And this is how we instantiate the buffer type, because we can already instantiate a slice using this notation, so we can do it with a buffer as well. And then we do some operations on it. I'll go back to that one. That's how, just a standard reference to an item in a slice and calling a method on it, nothing exciting. And then down here, there's a nice little bit here because this is a shortcut that you get in Go. You don't have to specify both ends of a slice if one of the ends happens to be the end point. So, but anyway, which in our actual practical code, we'd normally shorten that up because we import the whole of the integer namespace into our current namespace with this statement, and then the code becomes a little bit easier to follow. So there's no more references to integer down here. Right. Now, this here, this is another type, vector, that's actually based on a structure that contains a buffer type. It's not reusing the same memory layout. What it's actually doing is saying there is this structure of data, and I've put this in it. And this is anonymous. What that actually means in terms of Go is we've just embedded this type. This is as close to inheritance as Go gets. We've embedded a buffer in a vector. So a vector knows how to do all the things that a buffer does on this buffer. But we can't tamper with the buffer that's contained in the vector by... I'll see if I can develop that point later, because there's a lot of stuff to get through. But this is basically how you do type embedding. And this, yet again, is a method set on the embedded type. And the only real noticeable thing here is, yet again, these are pointers. I'm playing with the pointers to the type, not the type itself. So I'm also referencing this via a pointer. There we are. Right, so we end up in Go, we end up with a type model that looks like this. We have a memory layout that's actually the underlying memory that's being used for the type. We have a method set, and we can have any number of embedded types within a type. And that creates a static type. So that's the full static type system in Go. And this is the point at which C++ programmers will be going, oh, that's quite good, but you can't do proper inheritance. Fine. Now the clever bit. This is just a method set. An interface just defines a set of methods. Now, what this is equivalent to in Ruby would be when you send a message to an object in Ruby, you then can check that, well, you can send the message response to ask if that object knows how to respond to a message. And that's not a finite guarantee, because that object can decide to stop responding to the message after you've asked it. But that's how you would test to see if an object conforms to a certain kind of interface. Well, in Go, all of this information is stored statically in the runtime. So it's all available to be able to infer type at any point. So I can ask at any point in the program, is the type I'm playing with actually an adder? Does it have all of the method set that's defined for an adder? And type inference will then go and figure that out. I don't have to assert it anywhere, which is, it's a bit more like, it's sort of like, it's like the way that VB did interfaces, only if they'd been done properly. Because VB interfaces, you do have to assert, and I always wondered why, because it was obvious you had all the information. But anyway, there's one other little wrinkle in here. This thing here, this is the blank interface. That refers to any type, regardless of its method set, which means it also refers to all of the built-in intrinsic types. So, and here's an example of actually implementing a type that implements the interface. This is just another use of an int type, and it's a very simple one. We've got 4 methods back there that a type has to implement to be an adder, and we just implement them. They don't have to. This could be in a completely different package. It doesn't. This code could have been written 4 years before the interface was defined, but any code that uses the interface would automatically pick this type up as compliant with it, which is a great way of allowing for reuse in libraries. Down here, I've got a little couple of tricks I'm going to show off. One here, increment. That's a statement. That's not an expression. So I don't know if you've ever been involved in any of the arguments in the Ruby world about whether we should or shouldn't have a C++ increment operator, which we don't. But in Go, it's a statement. So it doesn't have to return a value, so it makes sense. It doesn't make sense in our world. And up here, this is the most bloody-minded way there is of creating a 0 value for an integer. This actually creates a pointer to a 0 value for type int, and then dereferences the pointer. It's in there for people who read the slides and you want to see a silly trick. But everything in Go, because it's garbage collected, is also given a 0 value when it's created. So we never normally have to worry about giving 0 values to things. This is another type that will also implement the interface, and because we've done the methods. But there's a difference, obviously, in that this iadder, this implements the interface plus increment, which means it can be used in places where an increment is understood to be available, whereas the fadder can't. But if we come down to a piece of code that actually shows this in use, constants are all perfect values, so you don't have to actually specify floating point constants to assign to floating point values. It's a stupid little thing, but here we are. Now, this is an example of writing a test. There's a section further on about testing, but I wanted to sort of show off a little bit to start with, because it suits this example. And in here, what we're actually going to do is we're going to define a variable of the interface type. Now, internally, that's stored as 2 pieces of information. And this is almost identical to the way that the V8 JavaScript runtime works. It's got a 32-bit field that is actually a type specifier, and a 32-bit field that is either a pointer to the type, or for primitive type is the type value itself. And down here, we can assign the iadder, because that will work because we know it complies with the interface. We can also apply the fadder, because that also meets the interface. So we've got something equivalent to variance in VB, or sort of equivalent to void pointers in C, but with semantic checking. And then we can quite happily just call those methods that we've defined. Now, there's an interesting little thing here. See this? This is actually a type assertion. Now, when I specified the interface for result, it's too far back to be worth going to. When I specified the interface, I specified it as just passing back an interface value. That we wouldn't make any assertion about what the content that was passed back from the method was. This is how we actually say, well, look, this had better be an int, because we want to do some int stuff with it. And in this case, if it's not an int, I can say, well, it's not an int, and do something. In this form, just here as a single bold statement, that will actually cause a panic if the type assertion fails. But there's also another form we'll see later on that actually will return you whether or not the type assertion passed or not, which allows you to do more sophisticated filtering in line as you go. So let's see where we get to next. And yeah, that's all very unexciting. Now, we've got a different rabbit hole with Go, because an object has known static type, which it doesn't in Ruby. The fixed type is determined at link time, because it's fully statically linked as well. You don't have any, Go doesn't support any dependencies on third-party libraries at present. Everything is statically linked, which is a plus thing and a minus thing, so we won't go into that. You cannot create new types at runtime, which I find very frustrating at times, because in Ruby I create a lot of new types at runtime. It's one of the ways in which I minimize the amount of code I have to write, but you can't do that in Go. So the dynamism is actually bounded to a fixed set, and that means that ultimately computer scientists are happier. A lot of the time, actually, I found that I'm happier, because a lot of kinds of errors I used to sort of have lurking in the back of my mind for special cases, I don't have to worry about. I feel a lot less need to use an exception mechanism in Go than I feel in Ruby, although I also don't have the exception mechanism in Go I have in Ruby, so that's a bit of a mixed blessing. Now, testing is a built-in part of the language, so I'm going to show off. I'm just going to show a little bit of code first that I'm going to stick into this buffer type that's actually going to help with the test I'm going to write. And here you can see I've got a buffer. I'm going to compare it to another buffer. I'm going to return a Boolean value. I can actually specify variables here as part of the set of return values. And Go supports multiple return, so I can have 3, 4, 5, however many variables I like along there. those would all be initialized to the 0 value as long as I specify a variable. Down here, I'm going to be returning a true out in some circumstances. This is how I find out the length of a slice. Nothing exciting there. This is a basic for loop. Do not be fooled by this. This looks just like a basic for loop in C. For is a lot more flexible than that, and I'll show some other syntaxes in a while. And so I'm just going to go off and use that. Oh. For those who aren't familiar with for loops in C, this defines some variables that live in the particular scope that's defined by the for loop. That's a test to see whether or not to do the next iteration, and that's just a statement that happens afterwards. Once you've done the iteration, to change a value or whatever you want. You can put anything in there you like. Testing, we use a package called testing. It's part of a tool called gotest. Now, technically, testing isn't an available package in the language in the way that excuse me a moment. London's been a little noisy this week, so anyway, so testing is sort of a pseudo package. It's actually a package that's only really understood by the tool gotest. And basically this will go through, and all Go programs are built with a make file. It will look for any file that's got an underscore test on the name of it, and then any function in there that's called test something or other is a test, and it will check to see if that test passes or fails, or at least it will run that test, and it's up to you to do the checking bit. So down here we've just got some boring stuff. I always import my testing packages into the package I'm actually testing. This allows me to do internal tests, because otherwise, if I don't put them in the same package, I can't. There's a difference between public and private functions and variables, etc. in Go, which I haven't really discussed in this talk, but it just makes certain kinds of testing easier. Here you can see some literal instantiations. We're just creating our vectors, and then we're just using a switch statement. Now, switches in Go are interesting compared to in C, in that they will do every successive case statement, until they find one that succeeds. So they're sort of halfway between C's idea of a switch statement and Erlang's idea of a pattern match. And some very clever things can be done with that. And here we're not doing anything exciting, though. We're just making sure that something works. These two test cases should both actually fail, and I've used this word fall through, because cases do not naturally fall through if they succeed. They only fall through if they fail, in which case this code wouldn't be run on this side anyway. So anyway, we'll skip past that. It's not very exciting. This is an example of a simple make file for making this particular program. And here's an example of how to do benchmarking, because gotest supports benchmarking out of the box. It does benchmarking by looking for these benchmark functions. It's got an odd little idiom for doing. Hold on a second. It's got an odd little idiom for doing benchmarking. You've got to love it when people go out and leave the washing machine on. Go's idea of how to do a benchmark is to figure out how many times a particular thing happens in a second. So this value b.n, that's actually a variable that it will run this loop with that set to 1 to find out what the basic time for doing that particular operation within it is. And then it will figure out how many times it ought to run in a second, and then it will run it again with that as the limit. And then from that, it will tell you what it thinks the actual time frame for benchmark is. It's a little strange, but once you get used to it, it's actually very handy. And you can start and stop the time if you want to, but I don't really find it, having enough initialization work in here to make that worthwhile only tends to occur if you're doing sort of micro benchmarks. So it's not really that relevant. And then here, this is just how you run it. That says we passed the tests, and so it goes on, does the benchmarks. So for vector swap on my particular machine, this was done on a netbook, it's 8 nanoseconds to do a vector swap with the way I defined it. So Go's reflected. Most of this talk is actually going to involve reflection in one way or another, because a large chunk of this talk is actually getting to the point of showing you how to do distributed map reduce. not necessarily well. I mean, it's not a lecture on map reduce, but it is a way of demonstrating concurrency in practice and so forth. So reflection is handled by this reflect package. And in this case, you see all of these places where I'm referencing in. Value of will find out the reflection type of something. Slices and maps are just understood primitive types. And we can create those dynamically at runtime if we know the type. Yet again, I mean, I generally, if I'm using reflection, I just import it into the local namespace. It makes the code that follows a lot easier to follow, because suddenly, you know, it's all nice and in your face, so to speak. I do a lot of work with reflection, so I also object to the extra 8 letters worth of typing. Here again, we've got another switch, but this is a slightly more interesting switch. This switch creates a scope. And in this scope, I'm going to be using this value v, obviously. But I can also, once I've created this value, this reflection value, I can then find out what kind it is, and I can do stuff based on that. This is a relatively new system. They changed the reflection system about 4 months ago. Prior to that, it had involved a lot of runtime allocation, and it was very slow. And these days, it's starting to feel a lot more sophisticated. Here, yet again, the purpose of this function is just to allocate something based on a random object that's passed in and some idea about what size it is. And here, this is if you're familiar with variable args, this is how, you know, Go does it. In Ruby, we use splats, and in Go, we use ellipses. And I'm only interested in the first argument anyway. I just want to know if there's a first argument, in which case I'll say, well, that's the new size I'm looking to play with. Otherwise, I use the pre-existing size. Nothing exciting there. It will just return whichever kind of type I want to create. With the slight wrinkle, I have to turn it back into an interface, because everything in reflection creates reflection values. So you then have to take the interfaces from them. But yeah, so nothing really exciting there. This is a little more interesting, because this is a very basic start towards how you'd write an exception system. Throws panic basically will take any old closure, because every function in Go is a closure. Even methods can be converted into closures if you know what you're doing. And over here, you know, I'm just going to say, didn't it throw a panic? And defer is basically like an at last in C, or there is at last lurking in Ruby, but I never use it. So these functions will then run in reverse order to the order they're defined in. And all this is doing is actually, you know, doing a quick test to see whether or not there's been a panic. And panics will always return a value unless you yourself panic with a nil, which is a handy way of doing catch throw. So anyway, and then so we did a function, we do some stuff. This is just basically testing that. So you can see down here, I can use throws panic in line with a closure. And this is genuinely a closure back to that. So we're using that particular memory slot. And yeah, again, I'm using a type assertion there. That type assertion will panic if the type that comes back isn't a slice of ints, in which case, you know, I'll know I've made a mistake. So this aspect of language takes a little while to get used to the syntax, because it looks a bit ugly, but it's very flexible. Now over here, I mean, the duplicate is just going to go off and do a clone. It's not very exciting at all. It's just a bit of code that shows you have access to the ability to copy random objects to random objects in reflection space. So, and that's slightly more complicated with maps than slices. This thing here, I told you that for would get slightly more complicated. Range, given a map, slice, or channel, will just automatically iterate through all of the elements that come in from that map, slice, or channel. With maps, the order isn't defined, but with channels and slices, it's, you know, from lowest to highest. And this is just basically a way of setting a random, you know, copying across all the items in a map. Now, Go is a systems language, and I'm probably not going fast enough with this. Will people object if I speed up? Are there blank stares out there and people with their brains dribbling out their ears yet? Because I don't normally do this with this many slides. So, okay. I normally point at things a lot and walk around manically, which distracts people. Okay, Go is a systems language. Now, to me, a systems language means I should be able to get down to the bare metal in absolutely every way. And on the surface, Go is a little safer than that. It's designed to not really let you get down to the raw metal unless you really need to have to do it. You know, because I mean, Google are really pushing it as a systems language for using on servers, not as a systems language for embedded systems. So fair enough. This code comes from a package I've written called raw, which is basically for those times when I genuinely need to use raw chunks of memory, the way I'd use a raw allocated void pointer slice array in C. That is not a common occurrence, and I really don't want people using this code very often, but it does show that you can literally walk completely past the type safety system and completely past the garbage collector as well, without actually breaking it, which is the good bit. So what we've got here is, obviously, I'm importing the reflection stuff because I'm going to use that. And I'm also importing this package unsafe. Now, this isn't really a package. Unsafe is actually a compiler mode, which just happens to be presented as a package, and that has about 6 methods that are functions that are associated with it. And which most people, well, the documentation is very sparse. So if you want to understand this stuff, I suggest probably looking through all the slides I've published on SlideShare, because I've probably written more about this in terms of actual code written than anybody else in the Go community. So here I want to find, I'm going to basically store the value that's kept by the runtime for type. In this case, the type of any old byte slice. And if I ask the runtime to create me a byte slice with a nil value, it will go off and it will create a 0-length byte slice with no underlying data array. It's happy to do that. And I'm going to be using that bit of information later on. And I'm going to join that with a bit of code. I'm not going to show an example of this in use, but I'm also going to define an interface that allows client code to short circuit what I'm doing and provide its own way of creating a byte slice. That way, my library, both on the one hand, can pick up, well, my library can use type inference to pick up things that already understand how to turn themselves into a byte slice, and then I don't have to worry about it. I think that may effectively be Go's inheritance model, for want of a better way of thinking of it. Down here, I'm going to do some stuff using a reflected value, and I want to make sure that it's actually valid, because the reflection system will tell me if a value is actually valid and can be used, or is actually garbage and shouldn't be touched. And I'm going to make use of information I can get from the type of that particular value to figure out a size. And a slice header is quite an interesting thing, because it sort of bridges the gap between a language in which all arrays are declared statically with static size, which Go is, and languages like Ruby that just allow you to play merry havoc with the size of an array. So a slice, basically, it has a fixed sized array underneath it, but that fixed sized array is hidden and you can't normally get at it. And it's normally presumed to always be constant. Whereas what we're about to do is say, well, we can put any array we want in that space as part of what we're doing. So this is slice headers, and slice headers are very, very cheap to use in the language as well, because they literally are just a pointer and 2 ints, which refer to the length and capacity of the array. So down here, a value also, in many cases, but not all cases, has a physical address associated with it. So the unsafe address is the physical address of the actual data on the memory. So we want to get at that. So I'm sorry if this is all a bit low level compared to all the Rails stuff that tends to predominate, but I can't help that. I haven't got a good Rails-like example for this. So over here, we're going to basically create our own slice header. There's a naming mismatch here. This wouldn't actually work. There should be a reflect dot before that, because you can't have 2 things in the same namespace that are different. But it wouldn't fit on the slides readably. So down here, creating a slice header is actually very, very simple, and also very, very dangerous, because we're going to take one of those unsafe address values, locations, and then we're going to turn that back into a pointer, and we're going to cast the pointer as a slice header. This starts to look a lot like C, because this is exactly the sort of malarkey. This effectively on this side is a void pointer, and then this is a cast on this side. We never have to do this in Ruby. I mean, we don't go near this stuff. unless you use Ruby DL and you play with byte buffers or whatever the Ruby FFI equivalent is, you never ever see code like this. So it's this is the proof we're in a systems language. So with interfaces, we can actually find out what the element is, and even though an interface we can't reslice, we can still have a go and see if we can reslice the content of it. And this bit of code down here is very unexciting. This is just a scalar to make sure that the slice header is resized to the right size and float 64s all over the place to make sure that we get the most accurate conversion we can. Byte slices. Now this is what's actually going to do the body of the work. This is what's going to create us our byte slice. And we don't have to really do any work if we've got, well, actually step back and rephrase that. This is going to do the byte slice. It's going to take a random thing. We don't care what that is. And it's going to return a byte slice, we hope. This here, this is called a type switch. And what happens is that we ask the runtime to figure out what type I is, and then to assign a new value to I in this scope that is actually of the correct type. And then we can check the type. And then off of the type, we can then use it naturally the way we'd use that type. So for example, here we know that I happens to be a slice of byte. So therefore we just return that slice of byte. Here we know it's a memory block. So we ask it to go and run its byte slice routine. This is still a lot more hard work than if you were doing the same sort of tricks in Ruby. But compared to doing these things in C or Java, this is much, much simpler. Far fewer void pointers flying around anyway, which has got to be a good thing. Down here we've got an example of how to do the same thing with a string. Now string is interesting because string is stored internally as actually as a slice of bytes, but that's actually wrapped up with a type above it that claims that it's actually a slice of integers because Go uses UTF-8. So there's a string header that we can get at. Oh, right. Let's go back one. Here we get the string header. Here we take the address of that and we turn that back into an unsafe pointer. And yet again, we've just done a cast of this to a pointer to a string header, and on top of that we dereference it, and suddenly our string becomes a byte slice. There's actually a much simpler way of doing that in inline, which is you can just cast a string as a byte slice. But this code is also intended to demonstrate to people how to do these sort of tricks. Down here, yet again, we're going to take this unsafe pointer to the header that we've created here. And this is lovely. This is the most dangerous line of code in the entire presentation. We're basically just going to tell the runtime to say, you know what a byte slice is. Well, why don't you just take all of that, turn it into a byte slice, and then assert it really is a byte slice? That's belt and braces. That's so it would throw a panic if it's not. But to be honest, it will be, because unreflect doesn't know how not to turn that pointer into a byte slice. And so anyway, that's the reflection system and all of the insanity you can do down there. Now, most people seem to be interested in Go that I meet because of the concurrency aspect, because Go's basically got a nice communicating sequential processes concurrency model. And there's an awful lot of power to be had out of nice, simple data flow programming, which is what CSP encourages, because it means that you don't have lots and lots of shared mutable state. That's not quite true in Go, and we will touch upon that as we go. But here's a simple example of this is the one bit of code in this presentation I ripped off from someone else. This is an example a rewritten example by Andrew Gerard, one of the core team, of how to write a random number generator. So it doesn't look like a random number generator, but it's a random number generator. So I'm going to introduce the concept of channels. Now, channels can be one way or two way. And I don't actually tend to bother in my code specifying them as one way or two way. I just specify them as channels. The direction of a channel is not actually part of its type, which is quite strange, really. And here I'm going to actually create a channel value of that type. Now, this is a synchronous channel. And I can state that this is a synchronous channel because it has no buffering space allocated. The only difference between whether a channel is synchronous or asynchronous in Go is whether or not you give it a buffer. And that also isn't part of the type. So you can use a variable with a synchronous channel at one point and then an asynchronous one at another point and still use the same variable. And I'm just going to sort of demonstrate here how you spawn off a Go routine. Now, these are basically functions that run in parallel. They're not a thread. The most important thing to say is they are not a thread. Threads in most languages are implemented using pthreads, which has this annoying 32K stack, which means they're quite expensive to allocate and launch. And B means that they're also patched into the actual operating system runtime normally, and operating system scheduled. Now, that's not necessarily a problem with modern operating systems, but even 3, 4, 5 years ago, every pthread that you ran in a Linux program was treated identically to a process that you ran in a Linux program. There was no difference. So if you had a massively multi-threaded program, you effectively had a massively multi-process program. It's just they were anonymous processes. In Go, a thread has a very small stack in comparison. It's 4K. It's also got a split stack, which means the stack will grow and shrink as time goes on. In fact, Go uses split stacks throughout the runtime. And an awful lot of several different Go routines can all live in the same thread. The scheduling is handled by the language runtime itself. And mostly that's on the basis of, is this something that's going to block because of I/O? Or is this something that, we can quite happily randomly pick which one to do next based on what's got work? So it's a simple scheduler at present, but it's surprisingly effective. So this isn't just a function. This is also a closure. 5 minutes left. I think we can do it. Okay, this is also a closure. So, okay, we'll speed up. This is also a closure. So that means this does have shared mutable state within the scope it's in. That's best to avoid. Now, coming down here, I'm going to use that limit to just take a certain number of values out. This select statement, we missed a bit there. No, we've missed a slide somewhere. Okay. This C here is the same as this C here is the same as this C here. As I say, that's a closure. They're all the same thing. So you can see there's potential problems with this particular bit of code. But this will randomly pick zeros or ones, and they are picked at random because there is nothing here that is blocking, and the scheduler runs at random. So here, I've actually introduced a new scope. So this in now is no longer sharing the same scope as that C. So it's no longer a shared state problem. Oops. And this is just the operator that pulls something off a channel. So select is pretty much like a select statement in a Unix program, which isn't surprising considering Ken Thompson and Rob Pike are developing the language. So I won't go into depth on that. This is how you then do an allocated buffer, one that's got an asynchronous buffer for a channel. So we'll skip past that. This is how you actually state that a certain function is a type. So I'm going to have to really race now because I want to get this bit done if I can. Here, I'm going to skip. This is just an example of how you would actually say that something takes that as a value. I'm going to skip past this set of slides because then nothing really exciting going on. Although that's a common idiom, so it's worth looking up later. Here, I'm going to define an iteration. An iteration is a function, but I'm not interested in it as a function. I'm interested in it as a function that I can store away and apply other functions to. Right, so I'm going to use a 2-level dispatch that I'm going to create myself. And the main thing that this is going to create, this iteration, every time it applies, is going to create a channel. And that channel is going to kick out values asynchronously based on running the function. This is how you do an iterator. And down here, this is how you then turn that into an each. Now, I've got a guarding statement here, signal source. Those just basically create a done value, and then they wait until that done value comes back. That's on the previous slide. And this is just some nice boilerplate to do the waiting. This is a combination, basically, is the meat and bread of doing a reduce. Right? So I'm going to use a results channel, which is a channel of interfaces. So channel of any old values you feel like. And I'm going to use an iteration, and I'm going to iterate through all the items, and I'm going to do that off in its own Go routine. So now I've got 2 levels of concurrent indirection. I've got this all runs all of its work in a Go routine itself. And now I'm chucking it off in a Go routine, and I'm waiting on a value here that will be the result value out. So I can multiplex off. I can create complex multiplexes very easily in Go. I think we're going to have to skip past the transformation. Transform is the same basic concept. So bam, 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 bam. This is how I would then, from this, get an iterator. So I can actually store off an iteration for later usage. Now, there's a lot of stuff going on in here that I've already referred to in the previous section about reflection. And so I'm not really going to cover that again. But as you can see, I'm just creating iterations, which are functions that are closures that I'm chucking back to store for later to apply other functions to. So we're fully deeply in the world of functional programming on that side of the language. And this is just an example of using the transformation and the combination. Right, here I'm just basically going to do a doubler. I'm going to map the values on that transform. And then sum just does a combination. Okay, we are so close. So I suggest going and reading the other 35 slides or so on SlideShare. 352 slides in this deck, so that's 10% the way off. Right, firstly, I'm already in the IRC chat room, so if you want to come in with questions there, I'll be there in about 10-15 seconds. For anybody who wants to talk about this stuff in more detail, I'm on Google+, Eleanor McHugh. I'm the only person, probably the only person on Google+ who's both called Eleanor and into Golang as it's normally referred. And I'm available to huddle or do that whole video thing if it works. And I'm just going to take this to the very last slide, because this is where you should go. Oh. Oops. Right, very last slide here. This is where you should go to find out more. Right? So that's the Go web homepage. Anything to do with Go is normally tweeted on Twitter with Golang. That's also a word in Philippines, so you get some strange things. That's where all of my GitHub projects live. There's some really mad Go-related projects there. And this is where you can find the slides from this session, all 352 of them. Enjoy.